Hi, our topic for today is trees, rooted trees and binary trees. By the way, this topic is very important for computer science because, for example, trees have a very interesting property that actually each node in a tree has a unique address, and yes, and you can follow the history of every node from the root. Usually the tree has a root, so that's why trees are very often used for storing the data for the databases. And then you'll see in next section 7.5 we'll also talk briefly about the way to do search algorithms through a tree. But let's make precise definitions and then get some examples of trees. So definition 7.4.1. A graph is called a tree if it is connected and has no circuits and no loops. A vertex of degree 1 is called terminal. All the other vertices, all the others are internal. Alright, so let's see a few examples. A, B, C, D, E, F, connected. This is a tree. Why? Because it is connected from every vertex of this tree. We can arrive to another one via a path, and then there are no circuits. So there's no way to start from one point and then come back to that one using a path. And then what about this one? A, B, C. Just I made this example. And here is the one. No, and this one, yes. Why not? Because there is a cycle, and that cycle is A, B, C, F, A. So that's why it's not. All right, proposition. Proposition 7.4.1. A graph is a tree if for every two vertices there exists a unique path connecting them. We'll exercise improving. Why? Because what? If graph is a tree, then since it's connected, so G is a tree. Since it's connected, for every two vertices, A and B, there exists a path connecting them. Why is it unique? Because if from A to B we have one path, and then we have another path, then what can we do? Go from A to B in no path, and reverse it from B to A, and here's a circle, which would be a contradiction. So if you have two paths that would reach contradiction, two different paths that would produce contradiction, so that assumption is false, so there must be a unique path. The same way here, if there is a path, a unique path, so the same way. It's really not worked, right? It's basically the same argument. All right, here is an interesting and very easy theorem. A nice exercise in induction. Generally now, you know, whatever we learn, we also use it to kind of practice the skills we develop in the beginning, and that was to write statements in a precise mathematical language and to be able to prove simple ones. So here is one, A3 with n vertices has n minus 1 edges. For example, this would be a good problem for a final, because this is not absolutely trivial, but it is fairly easy to prove. Why would that be true? We'll do by induction. Prove by induction. On the number of vertices, on n. So if n equals 1, then true. Why? Because we have only one vertex and there are no loops. It says here, no circuits and no loops. So that means no edges. So that means the number of edges is 0, number of vertices is 1, which is exactly, we have n minus 1 edges. Now assume true for n equals k greater than or equal to 1. And try to prove for n equals k plus 1. True for n equals k plus 1. So let G be a graph with k plus 1 vertices. First, we want to show something that would be a lemma, but it's very simple, so we don't need to formulate it as a separate statement. And that is, G must have at least one terminal vertex. Why? Because here it is. We start with the vertex, A1. Then, since the tree is connected, this one is connected to some A2. Whenever we can connect, we connect with some A3, and so on. So we are just building a path as soon as we can until we stop. Do we need to stop? Yes, because this cannot go to infinity. We only have finitely many vertices, so at some point we have to stop. So AS, when we stop. And as I said, it has to stop because otherwise we would have infinite graph. And then what? Now we claim that this last one in the path is terminal. AS is terminal. Why? Because it is connected here with AS minus 1, and that's the only connection of AS. Why? Because if AS has no more connection with the new elements, because otherwise we wouldn't start. So AS, because no connection with new elements, with other elements, I mean. Because otherwise we wouldn't stop. We stopped exactly for that reason, because there were no new elements. And then what? No connection with the old ones. Why not? Because if you make a connection with one of the previous ones, then we would have a cycle, and so AS has no more connection. So the only connection AS has is with AS minus 1. So degree of AS is just 1, so AS is terminal. And then what? Now it's very easy. We cut off AS from the whole graph, not only from path. So consider G without AS. And of course we cut that edge that connects AS. Now what? G minus AS has K vertices. According to inductive hypothesis, it has K minus 1 edges. And it is a tree. It's still connected. We didn't lose connectedness. We didn't build cycles by cutting someone. So it is a tree, and we can call inductive hypothesis, so it has K minus 1 edges. So G has what? Those K minus 1, and that one that we cut off, one here, plus 1, which is K edges, and that's what K plus 1 minus 1. So we proved our statement. So here it is, we proved it by induction. So you see there is a natural connection between number of trees, a number of vertices, and a number of edges, and that number of edges is one less than the number of vertices. All right. We also have an interesting reverse of this, converse of this theorem. So converse is theorem 743. It's very easy to prove. So a connected graph with, I'd like to keep it here. So with n vertices and n minus 1 edges is a tree. Proof. Assume the contrary, that there is a graph such that G has n vertices and minus 1 edges connected, but not a tree. So what's wrong then? It either has loops or circuits. So it means it has circuits and or loops. So what do? We keep cutting edge by edge, cut edges to remove circuits. Remove loops first. Loops do not affect anything. And circuits. Here is the danger. We might lose connectedness, but if you remember, we had a theorem in the previous chapter. If you have a circuit and then you cut one edge, then you cannot lose connectedness. Why? Because whoever needs that edge has an alternative path. How do they call that? How do they call it when they reroute your path in traffic? Yeah, there is a word for that. All right, so so that's exactly what you do. Like, you know, when they are repairing the street, then they just send you around to the rest of the circuit, and you don't lose connectedness. So that's what we do, to remove loops and circuits, but keep connectedness. And this cannot go forever because we have finitely many edges. So what happens at the end? At the end, we get a G prime that is what? Connected, no loops, no circuits. And it has what? And it has less than n minus 1 edges. Why? Because we kept cutting. It had n minus 1 in the beginning, then we kept cutting, so now we have less than n minus 1 edges. But this contradicts previous theorem. Here. Why? Because now when we still kept n vertices, so previous theorem says that your G prime must have n minus 1 edges. But we went down, so that contradiction proves our statement. So it's a nice, easy proof in both directions. It's actually a very nice exercise in our induction. All right, now what's special about rooted trees? Rooted trees have one vertex that's just designed to be a root of a tree. So definition 7.42. A rooted tree is a tree where one vertex is designated to be the root. Let me give you an example before I continue definition. So here it is, V0, then V1, V2, V3. So generally, I better tell you while writing. So we designated V0 to be the root of the tree. And when that's the case, then you actually draw your tree in a special way. So first, on the next, so you write it on top, for example. Then, on the next level, you draw immediate neighbors of a V0, and you call them V1, V2, V3. And then what? V1 has its own immediate neighbors, we call them V4, V5. And then V2, we have V6. And then V8, V9, for example. And then V3, V7, and then V10, and V11. So generally, by just taking one of them to be the tree, you can make hierarchy. So, so in that case, what for each vertex, we have the height of V is the length of the path between the root I forgot what I wrote. The height is the length maybe I want to say here of V, I don't know. Of V is the length of the path between the root V0 and the V. And that path, you remember, is unique, so each of them is actually assigned a unique height. So for example, for V10, what is the height? We need 1, 2, 3, so height of a V10 is 3. Height of a V11 is actually 4. And then height of a 3 is the maximum height. Is maximum of the height of a V for V and T. So in this case, h of T is 4. All right, and then there is certain terminology. For example, for V8, all these guys, V6, V2, and V0, we either say are ancestors or predecessors. Ancestors of V0, of V8, are V6, V2, and V0. And then V6 is the parent of a V8. V8 is child of a V6. Obviously, by analogy with family trees. And then what? So that's the definition. And then the elements that have the same height, we say that that's a level. So here is level 1, those that have height 1, this is level 2, this is level 3, and then level 4. And that's what's great about trees, that you can organize them by levels. And then, and what? Generally, like in the family history, every vertex in a tree has a unique history. You exactly know how that we came to that vertex, starting from the root. So really, rooted trees are very well organized. All right, and then what are the binary trees? Definition 7.4.3. Binary tree is a tree in which every internal vertex has exactly 2 children. So every vertex either stops, or if it branches exactly 2 times. It cannot just go simply, it cannot go 3 times, it has to go 2 times. And then here's a theorem, again, good one for final. I like this one because it's not complicated but needs little work, it's not trivial. So let T actually, I should correct this. A binary tree is a tree in which every internal vertex has at most, that definition we have notes, this changes, at most 2 children, and then when we say full binary tree, when it's exactly 2. All right, so let T be a full binary tree. Then what? T has an odd number of vertices. If the number of vertices is 2k plus 1, then k vertices are internal and k plus 1 terminal. We also call them leads, again by nature of knowledge. What is the proof? Proof generally says the following. Let me look at the tree from top down. I think we go from top down. So what? So let's look at the tree like this. So this one has 2 branchings, and this one has 2 branchings, and then let's it like this. So how many are here? 1, 2, 3, 4, 5, 6, 7, and that's true. And then how many are terminal 4, internal 3? So this example supports the theorem. Of course, this is not a proof. Proof is example just tells us how things are behaving, and we should never take it as a proof. But here is what we can do. Let K be the number of internal vertices. So this one is internal, this one is internal, and this one is internal. So K is the number, K, number of internal vertices. So each internal null vertex has two children each. So altogether, that means total, and they are not the same, because if two vertices share the same child, then we would have a cycle. If these two have the same child, then we would have a cycle. So they can never share the same child, so these are different children. So according to our counting principle, total 2K children. But then what? Everybody child except the first guy. So total number of vertices is those 2K that are children and the root extra, so total number of vertices is 2K plus 1. So from there, obviously, conclusion, because K were internal, 2K plus 1 is total, so K plus 1 are terminal. So very nice and easy conclusion. And then just one remark. In that remark, we said the following. Can we for every, so obviously, number of full binary trees, every full binary tree has odd number of vertices. Is the converse true? So for example, if I have, is there a full binary tree with 13 elements? Because 14, no, because we know it's an odd number. 13, and I made the general remark in my notes, but this will explain it the same way. Then the answer is yes. Here is what we can do. Here's an easy one, and I can actually prove by induction for every odd element. I can start like this. How many is this? 3. Can I make 5? Yes. Add 2 by branching here. This is a full binary tree. So what's that? 5. Can I make 7? Again, take one of them and branch it. So just take one terminal, branch it, that adds 2 more nodes, and you go 2 by 2. So 1 and 2, 3 and 2, 5 and 2, 7, and then 2, 9 and 2, 11 and 2, 13. So here it is. It's a very strange one, maybe very high actually, very tall tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's it. So you can always do that and do proof by induction. But we can say the following. Yes, but can I make one with lower height? And the answer is yes. Can we make one with height less than or equal to 3, let's say, or less than or equal to 4, less than or equal to 5, I have no idea. So generally, if you want to be most efficient with the height, then you want a tree that branches all the time. So here's what you would do. That's 3. Everybody branches. How much is that? That's 7. Actually, that full binary tree with the branching all the time has 2 to the n minus 1 elements. So this one has 7, for example. So I'm almost there. So 1 and 2, 3 and 4 is 7. My height is 2. Can I make it of height 3? Yes. What do I do? Full binary. But what's that? That's a little too much. That's 15. But then what do I do on 15? I just erase one of them. So erase as many as you need. 2 by 2, always 2 of course. To keep it full binary, here is the one with 13 elements. So here the answer is yes. The answer here is yes. And here is the example, height of this